Hi there, my name is Logan Patterson. I'm a master's student at the New College of Florida, and over the summer, I worked with a team led by Roger Dev to design test algorithms for causal model discovery within the HPCC Systems Causality framework. So, everyone is probably somewhat familiar with the idea that correlation does not imply causation. Causal statistics is a new field in which we're actually looking for that causation. We're looking for the direction at which causal effects occur, such as how does A affect B and how does B affect A. Now, there are a lot of algorithms that have already been developed to this purpose, but it can be difficult to compare them in terms of performance because they each have their own unique design conditions and testing situations. So my project was to create a centralized testing suite in which researchers and users can input a series of algorithms that they want to compare and run them on a battery of standardized testing conditions and have simple outputs that they can use to compare the performance of each of the algorithms. My ultimate goal then to that end would be to find novel algorithms and sort of compare them against the current framework's discovery algorithm using my testing program and see how well it works and how well each of them does. So algorithm testing in and of itself can be a little complicated, and so when designing this program I wanted to focus on three main aspects. The first is topology. Topology in this case is represented by the variables within a dataset. If a dataset has 4 variables, A, B, C, and D, the topology would be how A affects B, B affects C, C affects D, and so forth. And you can see a network sort of forming, as you can probably see in the results over to the right here. The framework already has several synthetic causal topology networks already included, and so I was able to use those and reference those in order to be implemented within my testing program. I also created a noise mechanism for a series of noise mechanisms for users to choose to run their models on. In this case, the currently included mechanisms are Gaussian and uniform because these represent the most common statistical noise distributions. However, users also have the option to input their own custom equations as well. Lastly, I wanted to focus on scoring metrics that were simple to understand and could be standardized across different algorithms and outputs so that, again, users have an easy time comparing their algorithms. I settled on SHD, SID, and AUPR, which are all structural comparison methods, and I think were fairly easy to understand within the outputs. I tested 3 algorithms against the framework's custom algorithm, ICGI, CDS, and GES. If you need more information, feel free to reach out and ask. This is an example of a data frame output from the testing program. So in this case, the framework's discovery algorithm was run against every single one of the topologies here. And you can see that it output the verbal description of the original topology graph as well as the algorithm's predicted topology graph. And then you have your scores here. There's also an average included at the bottom in case researchers don't want to do an in-depth look at each individual model and instead just want a quick glance at how their algorithms are performing. While this can be a little hard to see, I understand the main goal here is to, the main goal here was to show that you can see every single one of the topologies and their predictions sort of together in one go. So again, if you want a quick glance, you can sort of parse through and see that how your algorithm performs as topologies get more complex. Overall, I would call the design a success. The program worked as intended, all 4 algorithms were run successfully, and the outputs were easy to understand once it was done. So the only thing left is to grow, and I think that as more people use this and work on it, then it will sort of grow into a more robust algorithm and be very useful for HPCC systems. I think that there are also more complex algorithms out there that could be run using HPCC systems distributed computing networks, which hopefully then my testing program could be run on to sort of get better and more precise results. That's everything from me. If you have any questions or anything like that, please feel free to reach out. Otherwise, thank you for watching.